Okay, so welcome to our week of R introduction. This is going to be split into two parts for this lecture. So this is nearly everything you might need to know about R, part one, sort of a condensed, gentle introduction to how to use R and the R environment. So some things we're going to talk about today, starting out installing R and RStudio. We're going to try to understand the functionality of RStudio, understanding all of the different windows and panels, and knowing where to get packages and how to install those packages on your own. Because next week, we're going to be doing some differential expression analysis in R, and you're going to need some packages. So we'll learn how to do that. We're going to learn how to import data tables, and do manipulations on these data tables. Take out columns, add columns, just change the data into a format that is usable. Now, I'll say over and over again, the hardest part about doing R analysis in R is getting your data into the proper format. And then once it's formatted, everything's where it needs to go. Doing the analysis is usually easier. So being able to process that data frame is really essential. And then we're going to talk about R Markdown, how to set up an R Markdown and plug your code in and knit to a report. That is very useful if you're going to share your data with other people. So this is in my way a little bit. Okay, so some advice that I like to give students when they're starting out with R, even me using R now. I never start from scratch. Reuse code that you've written before or you borrowed from others. Find a package. All of the packages that I'll talk about, they have really nice tutorials. They call them vignettes, but it lays out step by step. What does your data need to look like? How do you do the analysis? And what does that analysis mean? So packages have really nice tutorials on how to use them, and you can copy and reuse the code from those tutorials. But let's say you're going to sit down, you're going to start your R programming script. So you open R Markdown, you open your file, you're overwhelmed. You don't know where to start. So just start with small steps. Set your working directory, think about what packages you might need to use, and load those package libraries. Import your table. Think about the one small thing that can move your script forward and do that. Think about, how do I need to set up my data table? Do that. So just think about, what is one more thing I can do to move this analysis forward? What is the most basic thing I can do? Something we're going to look at with visualizations is with this package called ggplots2. They make it easy to set up your base plot, just your most simple format of a plot, and then add extras. Do I want to add a title? Do I want to add a legend? So think about, what is the most basic thing I can do? And then what can I add on to that? Something that's really useful, even for me, is Googling it. Do you have an error? Do you need to know how to do something? Google it. Someone else has probably seen that same error before. If you're going to message me with help on the homework, I'm going to ask, what is that error you're getting? And the first thing I'm going to do is I'm going to Google your error and find out what to do to fix that error. So if you haven't done anything yet, Google how to do it. If you've done something and you're getting an error, Google that error. So that's my advice. Okay, so first off, my suggestion in this class is to install R on your own personal computer. If that's going to be a difficulty for you, let me know and we'll get you set up with using R through the supercomputer, which we're going to introduce in a couple of weeks. But for now, I really encourage you to install R on your own personal computer. First step is to install R. So, I don't know where my mouse is. Follow this link, r-project.org. It will go to here. This is the page, the website for R. And so you have to install R first. You go to download R. You choose a mirror. So the website that hosts R is set up with a lot of mirrors or different copies all around the world. So you choose one. It's probably faster if you choose one closest to where you are living. So let's see. Indiana. That looks like a good one. So we click on the Indiana. It's not a good one. Okay, so that didn't work. Let's try WashU. Okay, so here is a mirror of R to install. Choose your operating system. I've always said Windows machines. So I click on Windows, I click on install R for the first time and follow those questions along to install R. I'm not going to do it because I already have R. If you have Mac, it's similar. I've never done this before on a Mac, but figure out what your version of Mac is, install the appropriate thing, click through the wizard, I guess, install R. If you have trouble, I do have a link to a YouTube video. I think this is Mac based because, again, I don't have experience. So watch this video. If you're using a Windows machine and you need more assistance, look for a Windows R YouTube clip. It's my suggestion. Okay, so once you install R, you don't have to open it yet. You go in, you're going to install RStudio. So R is the programming language. RStudio is the interface that we're going to use R. So you follow this link. I already have it open. You click another link to download RStudio. Scroll down, scroll all the way down, download RStudio. Scroll down. We've already done the install R, but if you haven't yet, here's the link to it. And then second step, install RStudio. Here's for Windows. Here's another link for Mac and other ones. If you don't have Windows or Mac, they are here. So download that executable, run that, follow the steps to set up R and RStudio on your own computer, wherever that may be. I also have a YouTube link to see somebody install RStudio. So once you have those two set up, then you would be able to find, mine's just right here, RStudio on your desktop. It opens and it's connected to R automatically because you've installed R first and then you've installed RStudio. My version of R is not the most up to date. It's 4.2.2, where we are all the way up to something more than that. Yeah, 4.4.1. So when you're starting out, always install the most up to date R. And then as you work through, as you're working with R over the years, update R when it seems like you need to. I try not to update R a lot because then I have to go in and update all my packages, and that's just annoying. So I try to use a version of R for as long as it will get me. And then I end up running into some kind of wall with the package because it's been updated and my version of R is not good anymore. So I have to update my R, update all of my packages. But you're not going to have that problem in this class. So just install the most recent and run with that. Okay, so we've installed these two things. So I'm suggesting you install it on your personal computer. If you have trouble with that, there's also an option to use R and RStudio through the Ohio supercomputer. We're gonna do some command line analysis on the supercomputer later in this course, but if you search for, if once you have an account, you go to the OSC on demand, and there's an RStudio installed there that you can use. If you're doing something very computationally heavy, using OSC is a better option than using your own laptop. Okay, so you've installed R in RStudio. Now I'm going to give you a tour of RStudio. I've already said when you open RStudio, it's going to connect automatically to R for you. It opens up and you have these 3 panels. So we have our console, we can type commands. We have our environment up here. I'm hoping you can see my mouse, but it's up in the upper corner over here. And it's going to have all of your variables, any of your tables. We'll talk about what variables are a little bit later, but anything you create is going to be stored in your environment. Then in this lower panel, there's a place for plots. If we plot something from our command line, the plot, a little picture of the plot will show up in this panel if you don't print it out to a file. So if you just want a quick view of your plot, look at it there. There's also a window for packages. So we're going to talk about packages in a little bit. These are packages of functions that creators have made for us, the users, to use in R. It's very useful to our lives. So these are all of the packages I have installed. As you install packages, they'll show up here. There's also help. So this is very useful. If you're trying to use a package and a function of your package, you don't really know how to use it. We do table question mark, that function, it will pop up in our help window over here. Anything you need to know about that function. What are the things that you need to provide when you're running that function? What are some options? And what do each of those arguments mean? It goes through every single thing here. So those are the 3 useful parts of this panel down here. Something I forgot to say, up here in the environment panel, there's a history panel, which I find very useful. It keeps a record of all of the commands that you've ever run in R. So I'm kind of getting ahead of myself, but I'm showing you the different panels in RStudio. One panel that we're missing is our script panel. So we're going to go up here. We're going to click on this new file button and say we want an R script. We could also say file and new file, choose an R script, either way you want to do it. So we popped up a new panel of windows in our RStudio, and this is our script. So a script is where you're going to type commands that you want to keep. So down here in the console, you can type commands. They're not saved for later. But if you type them in our script, we can save this. Save it on my desktop. Temp. So anytime I want to run this command, I can open my temp script and it's there for me. As you set up your script, you can run the whole script if you click on source. I rarely ever do that because I want to run one line or a chunk of lines at a time. So if you want to run one line, you can click on this run button, run the current line or selection. So it just runs that. Another option is you're on this line and we do Control Enter and that runs the line. Another option is Let's have another. Get working directory. Okay, so we have 2 lines of code here. We're going to highlight both of them. And we're going to run them together. I did Control Enter. You could also click on the run. Either way you want to do it. We ran 2 lines of code right at the same time, one after another. So think about, how do you want to write your code and how do you want to run your code? Do you want to run it 1 line at a time? Do you want to highlight a chunk, run that chunk? So these are some options. I do suggest running scripts 1 line at a time because you're going to have errors and you want to know, when did that error happen in my code? And it's kind of hard to do that if you run a whole chunk of code. So keep that in mind. How are you going to run the script that you just wrote? Back to the, okay, so back to the slides. We have our console. We have our code editor, which is your script. We have your environment and history. And we have plots and packages and help. So just know that these are some of the options for the setup of the windows in your RStudio. If you want to change this around, you can. I never do, but these windows, you can minimize them, maximize them, probably control which ones you're seeing or not. Okay. So the first thing you're really going to want to do when you're writing an R script is set your working directory. And this is, where are you working in your computing space? I like to create a folder and have my script in the folder and have all of my files that I'm going to need for that script in that folder. So first thing you're going to need to do is set your working directory in your script so that R knows where to start from. If you're in RStudio, keep bouncing back and forth. If you're in RStudio, you can set the working directory through this GUI by clicking on Session, Set Working Directory, choose Directory, and then you can move around on your computer. I can go to Documents and choose something. I don't know. Choose something. And this is my working directory. I say open. You'll see this line of code was run in our console, but it's not in our script. We want to add this line of code to our script so that next time we open this script, we don't have to set the working directory interactively like that again. So we could copy and paste. Copy it. Okay, my laptop's not great at highlighting. Okay, we copy, we paste. Now, if we save this, it will be saved forever in our script, as long as we don't delete it. The other option is to go over to our environment and history window. You'll see, my face is covering it up a little bit, but here's our command that we just set up to set our working directory. And we could send that to our source script. It will bump it over. Okay, to source. And now it's over there. So however you want to do it is fine. If you want to just type set working directory and you know this path, I never know the path, but if you know the path, you can type the path and that's fine too. However you want to get it. Okay, I'm going to delete these. But R needs to know where to point to import all of your tables and whatever you're using. So we use set WD working directory to set your working directory. And you can check, am I in the right working directory, by just running get WD and parentheses. And that will print out the path from where you're working. Okay, so we've talked about RStudio and that it links up with R. We know that there are some commands. These commands are built into R that we can use. They're called functions. We can use these functions to read in tables, to do really simple, basic things. But very intelligent people somewhere have written groups of functions to do certain things. And a group of functions is called a package. And it provides an opportunity for these individuals to share their scripts and their functions with others. It's going to have code, it's going to have documentation, the functions, tests, anything that is needed to get these things to work. And they'll often even give you an example data set. You download this data set, you download this example script, and you can run it. And it's really nice to make sure that everything is working for you in your working environment. So you install a package one time and it's in your computer. But every time you open RStudio, you need to tell, maybe through your script, tell RStudio, load this package into my library. So install the package once, we'll see how to do that. And then every time you open RStudio, if you want to use that package, you have to use this library function to attach that package to your running instance. Okay. There are a couple of different places that hold these packages that you can install from. So the biggest one is CRAN or CRAN, however you want to pronounce it. But it's the official R repository. It's run by the R Foundation, and they're very strict on the requirements for these packages. So that's CRAN. There's Bioconductor. Bioconductor has very rich user, it has a very active user community. So the people who make packages for Bioconductor update these packages frequently. They're really supportive of keeping these packages ready for you to use. It's open source and they have criteria for submission. It's not as strict as CRAN, but it's pretty hard to get into. So that's Bioconductor. GitHub, it's very popular. There's a lot of projects there, but it's unofficial and unchecked. So sometimes these creators of packages, they'll have a GitHub and they'll have a Bioconductor repository for their package. They'll update the GitHub more often with maybe some features that are in beta version. So they're trying some stuff out. Sometimes the GitHub version works better than the Bioconductor version because it's just easier to push that version of the package to GitHub than to update it with Bioconductor. So we'll see some packages from all three of these places. And for your assignments, you'll need to install packages from all three of these places. This is what a package page from CRAN would look like. This is one package A3. I've never used it, but there's a PDF for documentation. There's a gzip tar file if you want to install it from a download. But normally we install packages from CRAN using this install.packages function. You give it the package name in quotes, and it will install this package for you. And then in a couple of slides, I'll give you a bit of warning of things you might encounter when you're installing packages. But this is the command line to install from CRAN. Here's Bioconductor's website. If you want to go look around, see all of the packages that are available. If you're going to install from Bioconductor, it has its own commands. So the first time you install from Bioconductor, you need to install the installer. It's called BioC Manager. It's stored on CRAN. So you install this manager, and then you use the manager to install Bioconductor packages. There's a website that lists all of the packages. Here's an example package. Whenever I'm installing a bioconductor package, I'll search for that package, bioconductor, go to the website for that package, and copy these commands in the black box. I copy that and I paste it into R. This will check my BIOC manager, make sure it's installed, and then it will install my package. That's what I do every time if I'm installing from Bioconductor. It makes it easier. I don't have to remember anything. So, okay, we're back here. Some things that students have run into problems with in the past is they're installing a package, but they assume it's a CRAN package when it's actually a bioconductor package, and they'll get an error saying there's no package with that name. So Google the package, make sure you know where it's stored, and so you know how to install it. If you're going to install any of these GitHub packages, you have to install DevTools first. DevTools is on CRAN, so we can use install.packages to get this DevTools wrapper. And with DevTools, we can install from GitHub. And the name of the package is usually so it looks like a path. It's the developer / the package name. So if you know your package is not on CRAN or Bioconductor, just make sure you have DevTools installed and loaded so you can install that GitHub package. These are the packages that we're going to use next week for our differential expression module. So if you can get started installing these packages, you're going to be ahead of the game. So there's 3 from CRAN. We saw the install.packages function, which would be used for these. These are from Bioconductor. It's actually wrong. DevTools is from CRAN. Okay, we're changing things in the middle here. Okay. It's live TV. Okay, so these are from CRAN. These are from Bioconductor. For CRAN, we know there's that function and we put our package name in quotes. For Bioconductor, search for this package name, copy that text in the black box, paste it into R, and it will install. Before you do the DevTools packages, install DevTools from CRAN, and then you can run this command, which will install our GitHub packages. There's 2 of them. So try these out. If you have any problems, let me know what error you're having, and we'll work through it. As you're installing packages, so there's going to install one at a time because it's going to pop up with some questions. Especially with CRAN, it's going to ask you to pick a mirror, and it'll use that same mirror through your whole session of installing. So it's going to say, these are all of the mirrors available for CRAN. Pick a number and hit enter. I don't know if it matters really which mirror you use. I just assume a location closer to me might be faster. So what you experience may vary, but pick a mirror, hit enter. Then it's going to ask you, it's going to check all of the dependencies for that package. This package needs to use the function. So it's going to check, do you have these packages installed already? It might ask you, can we install these packages for you? It might ask, so I see you have some of these packages already, but do you want to update to the current package release? And if you do want to update your packages, hit A for all, S for some. It's going to have you pick which ones, or N for none. The fastest route would be to just say, I want to keep my package versions, how they are, and say in. Then it will install any dependencies that you don't have already. It will install your package, and this will be good. You may see some warnings. It might say, this package was made for our version, something dot something. Warnings are fine. Once it gets finished running and everything, you can check. You can do library, parentheses with your package name in there. If there's no errors, you're fine. If there are some errors, we might want to dial back and check what's going on. Where did it fail? So let me know if you run into problems and we can work through it. Okay, so we've talked about RStudio. We've talked about packages. I've shown you a little bit about how RStudio works. Now we're going to talk about more classical programming topics, data objects, loops, just programming basics. If you had like C++, then there's similar things in the other languages. So data objects, starting out with. So a scalar is a data object that is just one thing. So it could be one number, it could be one character string, but it's one thing. You can have a vector, which is a list of things, two or more things, two or more numbers, two or more character strings, but that's a vector. You could have that's a one-dimensional vector. You could have rows and columns of things, numbers or character strings. This is a matrix, but all of these, they're just for one particular type of data. So in R, we have types of data, which include numbers, characters, integers, which are whole numbers, and booleans, which are true falses. So a scalar, vector, and matrix can only be of one type. So keep that in mind if you're trying to do that. There's a list, which is a combination of objects. So a list could be a combination of 2 or 3 different matrices. And one matrix could be a character string matrix, and the other matrix could be a numeric matrix, but they're all together in a list. It could be a vector and a matrix and a scalar combined into a list. Whatever you want. Lists can have different types of sizes of objects and different types of value types. What I use more often is a data frame. And this is what we classically think of as a table. So a data frame has columns of information and a row of like a subject. So you can think of a row as being for one subject, and each column is some sort of clinical information for that subject. And we have an example here where we have patient IDs. These are our subjects, and each column is some type of information. And there is a place for every single row to have a value for every single column. If it happens that there needs to be a blank space, we usually use NA as not available. But a data frame is what we call in R as our typical table, where we can have a mixture of numbers and character strings and booleans, whatever you want. Each column can be something different. Let me hide this video panel. Oh, whatever. Okay, you lost my face. Okay, I can't read what's under here, but I've already said most of it. Okay. If you have a file with all of your data in it, you can import that file with the import functions. These are base built into R, but they have a certain format that it's expected to use. I used read table most often. So this is that help prompt that we get, if we ask question mark read table, it tells us this is how the read table function is set up. At a minimum, we need to tell read table our file name, whether there is a header row in our file, and the separator. So what is delimiting our columns? Then there's a lot of options. You could tell it, use that first column as row names. So here's our row names option. And another possibly useful thing is whether to assume that any character string column should be a factor. And we'll talk about factors a little bit later, but factors are characters with defined groups. So it could be tumor normal, where setting it as a factor sets tumor as our main group and normal as our control group. With factors, we can set the order. If we decide that we want to switch it, we could have normal be the primary group and tumor be the second group, and that's set with levels. But if we set strings as factors to true, then when it reads in our table, it automatically sets any column with character strings, it sets them up as factors. And that's kind of useful, I think, later on. There's some other things. There's DEC, which specifies what are you using as your decimal place. So here we use a decimal place as a dot, but places like Australia, Great Britain, they might use a decimal place as a comma. So depending on where you're getting your data, what the default setting for that is, you might need to set what is the decimal place. You can also set what is your value for missing values. So normally it's going to be NA. Maybe you want to set a missing value as unknown. So if you set the NA strings to all whatever values might be possible in your data set, it's going to make your life easier as you go on. If you have a comma delimited file to read in, there is a preset version of read table that's called read CSV. And so we could check out read.csv. What are the options for that? It's pretty similar, but we don't have to specify the separator. So that didn't really work like I expected. Okay, it's down here. It is. So it's here. We have to specify the file. We have to specify if there's not a header. It assumes there's a header. But if there's not a header, we would have to say that. And it assumes, since this is read.csv, that the separator is a comma. So there's that. Okay, those are importing your data. So this is your data frame. And I've already been over all of this, but a data frame is a combination of vectors or columns that are all the same length. And each row is an observation. And the benefit of a data frame is that each column can be of a different type. We can find out information about our data frames. So the first very useful thing, I think, is we can say, what are the dimensions or DIM of our table? And it will tell us there are 5 rows and 3 columns. So you have an idea of how big is our table. How many variables are there? And how many samples are there? Another thing we can check is STR, which asks for every column in our data frame, what is the data type? So here we have 3 columns, measure 1, measure 2, both of these are numeric. And then we have the third column is names, and it's a character. And it prints off a few of the observations here for us. So we can see measure 1 is number, measure 2 is number, names is character. This gives us an idea of what the data looks like. Now, I don't have one here, but if we had a table, it would show up in our environment and we could just double click and it would open that table in our environment. And that would give us an even better view. It would look like this screenshot that I just took earlier. That is what would pop up when we click on a table in our environment. Now, if you have a column in your data frame that's a character, it's a good idea to have that character column be a factor. And that is because factors are a special type of character string that have a fixed and known set of values. And having known values allows us to set the order. We call them levels. We can set the levels of this factor and control what order they are presented in. So if you're going to set it right off the bat, when you're importing your table, you set strings as factors. But if you've already imported your table and you're thinking, I'm going to set this column as a factor, then we have our table $ column, and we use this assign string, or whatever you want to call it, to make this column a factor. We're using the factor function. We're factoring our table $ column and saving it back onto our table $ column. So that saves it into our table. Anytime we reference our table, that column is going to be factored. Maybe, so by default, our factor is going to be ordered alphabetically. And that gets us into trouble sometimes because we really don't want the factor to be alphabetical. So let's say we had low, medium, and high. And if we just allowed R to set up our factors, they would be kind of mixed up. It would, I don't even know. It would be high first, be low second, and medium third, I think. I can't do alphabets in my head, but yeah, I think that's what it would be. So if we were going to factor this val1 column, then we might want to set the levels, because it makes more sense if we have low first, medium second, and high third. So that is directly specifying the order of our levels, because we have knowledge, we're humans, and we have better knowledge than the computer of how our levels should be ordered. So that saves it into the column, into this order. If we want to sort our table based on these levels, then we could take our table and order it. We're putting this order, we're saying order these rows because it's in the first part of our square bracket. Order our rows based on our val1 column, and then save it back into my table. And my table would then be sorted based on our val1 factor levels. So we've already talked about this. We're going to skip. Okay. If you want a quick view of the column names of your table, you could just say call names of my table and it will print out, it will number them for you so you can know column 10 is overall survival in months, and it's named this with all these little dots in it. So this allows you to view the column names and maybe pull out the column name that you are most interested in. We've already seen this, but you can refer to your column within your table with this format. Have your table name, $, column name. And that's how you can refer to one column. There's a table function. So this could get a quick count of what are all of the unique values of column name and how often does each one of those unique values exist in my table. That's what the table function does. You can do it with one column. You can do it with 2 or 3 columns. It gets kind of messy, but I suggest 1 or 2 columns is very useful to get an idea of what are the number of records that belong to each value of my column. A table you can refer to based on indexes, and we format this when we're typing it out in our scripts as table square brackets. The row is the first number, comma, column for the second number, and then close the square brackets. So you can refer to one particular value in your table as row 747 and column 9, and it would spit out the value of those indexes. You can use a combination of this $, column name, and index. So from our table, we are choosing the column called Neoplasm Disease Stage American Joint Committee on Cancer Code. It's much too long for a column name, but that's our column we're pulling out, and we're asking for the 747th record or row from that column. You can filter based on these indexes. You can incorporate logic into that filter. So let's say you wanted to filter your table based on age greater than 50. So this is pulling out every row of our table where that row has an age that is greater than 50. And what it's doing is it's asking for every row, does this row have an age of 50? And it returns a vector of true falses. And you can kind of think about that as zeros and ones. So if your row has a true or a 1 for that logic query, then it's going to keep that row. If the logic was false, if the age is less than 50, then it's going to throw that row out. So this is a way to subset your table based on age. If you want to add a column to your table, there's a way to do it with cbind. If your table and your column you're adding is in exactly the same order, you can use cbind. I don't recommend using cbind because that's probably not true. So what you'd want to do is you would have doing this table, column, new column would be my table, maybe age plus 10. So this would be age plus 10. So it would do some math on the age column in my table. It would add 10 to it, and then it would store it into a new column called age plus 10 in the original table. It would make a new column. So there's all kinds of useful things you could do with this, but I'll leave that up to you. If you want to remove columns, I think the easiest way is to assign it a value of null. So my table, $ column 1, we assign it a null value and it removes that column. Maybe you wanted to remove more than one column, So in this example, we're using indexes. So we're saying from my table, we have these square brackets, and so there's a comma. So all of this information is in the column side of this comma, and it's saying remove with this minus sign, remove values 1, 3, and 5. And it's set up this way in the parentheses with a C. And that's how we refer to a vector. This is a vector of 3 numbers, and that's what's being fed into the index value of the column side. And with the minus, it means take it out. So that's how we can remove columns. We can add rows to a table. So let's say we have table 1 that has all of these values, and then table 2 has exactly the same column names, but it has rows for some new samples. So we can R-bind 2 tables that have exactly the same columns, but if we want to add new records. There's some other ways of doing this. Well, this is using R-bind. Okay, so R-bind is the best way to add new rows. If you want to remove rows, we have that same removing columns set up, but now it's in the row side of our indexes. So it's before this comma in the square brackets. We're going to remove this vector of rows 1, 3, and 5. We can also remove rows by using this subset function. So we have we're going to do a subset function. We tell it the table we're using, and we tell it what is the logic that we want to filter this table on. So we are asking to keep the records of this table where age is greater than 50, and we save it as our subsetted table. We're doing this calculation and then assigning it to subset table. And that is how we can filter our data frame. There are ways of merging one data frame with another. You need to look for a row that is common to both data frames. And I'll show an example later when we get into some R scripts, but combine 2 tables based on 1 row that you'll specify, 1 column. And you can specify the column that is shared between the data frames. So you can either tell it the name of your column, the column from table X, and the column from table Y, if they're different column names. You can even merge on row names. If you have the row names in your table X are the same as your row names in table Y, you can merge by specifying the column is 0. And I will show some examples of this later. If you want to use one of these fancier packages that has a built-in merge function, you can look into that. dplyr is a very useful package that has a lot of these alternative functions. It's part of the tidyverse, which is very, very useful. But there are different functions with different settings, and you can look into those for your own use. There's an example that I can walk through when I'm going into the R script where we can reshape data formats. So a table can be in a long format or in a wide format. And there is a package called Reshape2 that has some functions that can go back and forth from that long to wide format. So that's for later. Let's say you imported a data table, you did some analysis, you had some results, and now you want to save that data table to for the future. There are functions available for writing your data to a file. The one I use most often is write.table. You specify your data frame, your file. How do you want to delimit that file? I usually do a tab. You can also do a comma. You tell it whether you want to export row names and whether you want to export column names. A word of advice is if you're exporting both row names and column names, set row names equal true and column names equal NA. And this is something I experienced by struggling with it. If you don't do it this way, your columns are going to be shifted over one because it's not going to leave that empty space for your row names in the text file. So just be aware of this, or see it happen so many times that you ultimately remember to put it in. So you can also save tables and objects in your environment as a our data object. So here you can save one object into our data. You can save a couple of objects into our data. So let's say you have another script that you want to import to this our data object into. You can use the load function. And as beginning users to R and RStudio, it's going to ask you every time you close RStudio, do you want to save your environment to an R data object? I recommend not doing that. Just say no, and it will close your R script. If you say yes, it's going to save all of your tables, all of your variables into an R data object. And when you open the script again in the future, it's going to load all of those things back in. And I know I deal with some big tables, big variables, and I don't want those importing every time I open my R script. So it's okay to say no to that prompt. If you do have an instance where you want to save your entire environment to an R data object, here's that function for it. Save.image and specify the R data file. Okay, so we've talked about just using RStudio, making a script with a series of commands that you can run through. There is an alternative format for making a script, and this is called R Markdown. Let's see, what do I have here? So R Markdown provides a combination of text, which is informational for your reader, and code, and the opportunity to run that code, generate figures and data tables. And once all of that's laid out, you can knit, what they call knit, all of that into an HTML or a Word document that has all of the information, all of the tables and plots that you might need to share with someone else who is interested with what you're doing. So R Markdown provides an interface for that. If you want to get started with a brand new R Markdown, we would go to New File, choose R Markdown, tell it some information, my new script, that's my name, that's the date. What do you want the default output for this script to be? HTML is great. We say okay. And it creates an empty R Markdown setup for you. I think this is very useful when you're just starting out. Something that I like to point out. So this is in my slides, but it's easier to talk about here. So every R Markdown starts with what they call a YAML header. And this has information. Right now it has title, author, date, and what is the default output. You can also add more information. This is information about the setup of your R Markdown. Do you want chapter headings? Do you want little links on the side of your HTML to click to different sections of your R Markdown? So there's ways of setting that up. There's all kinds of options, and it's really kind of cool. Let me see. That's setting it up. It's looking at it. Okay, well, we haven't talked about it yet. Okay. So the YAML header is completely descriptive, tells R some important information about what to do. But the basic level, all it needs is this. And then you'll see this section is a little darker gray than the other one. And this is a code chunk. The code chunk, it has a name. So the name of this code chunk is setup. You can have an optional bit of information. Do you want to include this chunk of code printed out in the final HTML? So this is telling it, do not include this command line in the final HTML. You'll see another chunk of code. It doesn't have that include option. Another option here is echo. So the echo is saying, do you want to print the actual command in your final HTML? And here we're saying, no, we don't want this command plot pressure in my knitted HTML. So there are some options that you can include in your code chunks. They're completely optional, but think about who is the audience for your R Markdown report, and what do they need to see? Would the code be of interest to your audience, or is the audience just mainly interested in the results? What does the plot look like? What do I really need to know? Might be the difference of, are you sharing this to share your process of the analysis, or are you sharing this to share the results? Something that I've run into trouble with is when I'm making code chunks, I might copy this and paste it. And R is going to throw an error with this because the car's name for this code chunk is repeated. So we'd have to make it cars 2. Something else you can see here is there is a bit of text between our code chunks. And something that's really cool about this text is if you want to start a chapter, have pound sign, and the name of your chapter. And when you knit this into an HTML, this text is going to be larger than just your informational text down here. And you'll see this word knit. It has stars around it. And that will make the word knit be, I don't know if it's bolded or italicized in the final HTML, but it's going to look different. There are ways of formatting your text so that it looks a certain way in the final knitted product. And there's all kinds of informational guidelines for all of this. So if you want to know how to do something, I suggest that you Google it. I don't know all of the ways of doing it. So it's really very useful, but there is a lot of information out there on different ways you can present your information. Let's say that you're making this R Markdown and you know not to copy and paste the code chunks because you're going to get in trouble with the names being the same. The easiest way to add a new code chunk is this green square with a C in it. And that is the insert a new code chunk shortcut. We can also do, it says Control Alt capital I, but I've never done that. But you just click on it, you tell it, I want an R code chunk, and it will format it for you right here. This is the minimum that you need to make an R code chunk. So then you could type your code here in this code section, and it's not real code, so that it doesn't like that. But This is the section, the place for you to place your code. Now, if you're working on this R Markdown and you want to run through, check how things are running, you can see these buttons over here. This triangle on its side means run current chunk. It will just run this section of code. If you see this button, it's a downward gray triangle with a green line. It says run all chunks above. So it's going to run every single chunk of code that exists before this current chunk. It will catch you up. If you want to run all the chunks of code, I think run all. I clicked on run here. I can choose run all. But you can still run single lines of code. You have to scroll down and run all the single lines of code. I really suggest doing this because running line by line is the easiest way to find out where's the problem, what's not running like you think it should. So those are my suggestions. If you have your code, if every single line of your code is running and you know that it's all going to work, you have a pretty good idea. You can, if you see this knit button, there's a ball of yarn and a knitting needle. You push that. Oh, I haven't saved we need to save. Okay, temp. We've saved our R Markdown. Now we're going to knit it. We push that button. Do something. Yeah. So now it's going through. It's running all of our code and it's rendering. And this is the process to take our Markdown code and generate this HTML. It's a very simple HTML, but here's that pound sign chapter heading, R Markdown. You can tell it's bigger. Here's that knit word. Since it had star, star, knit, star, star, it's bolded. And then we can see our code chunks and what resulted from running those code chunks. And we have our plot. We don't see the command used to make this plot because over here, echo was set to false. This HTML, it pops up as you've knitted it, but it's also saved in this path right here. So if we close it and we want to go look for it later, it's just in your working directory as an HTML. So be aware of that if you're looking for it later. Okay, so I've said all of these things. The more pound signs or hashtags, depending on how old you are, you can call them either one. The more you have, this chapter title will be a subtitle. So 2 hashtags gets you the chapter title. 3 of them would give you a subtitle. This is talking about those code chunks. You can click on the C and choose R to automatically generate a code chunk. You can also type back quote, 3 back quotes, curly brackets with an R inside, and then end it with 3 more back quotes or back ticks, whatever you want to call them. You can optionally have a name for your code chunk. Just make sure that all of your names are unique and you don't reuse them, because that's messed me up before. Okay, and then finally, think about what you want to print to the final report. Set echo equal to true in a code chunk. If you want to print that code, echo equal to false to not print the code. Eval is another setting, whether you want to run that chunk of code or not. Include is if you want to run the code, but not print anything from that block in the knitted report. And you can set warnings equal to false to suppress any warnings or messages. Messages might be a different one. But when you load a library into R, it's going to spit out a bunch of, we're loading this and we're loading that. There's probably a setting you can set in your header of your code chunk to say, don't print all of that to my screen when I'm knitting my report, because it's not useful for the reader. It's important. It needs to be run, but the reader doesn't need to see that. So warnings equal false might do that. Think about who is your audience for your R Markdown. Are they more technical or are they more biological? And you might want to include more code for a technical reader and less code for a biological reader. Okay, so the things we have learned in this lecture: installing R Studio, installing packages, importing and exporting tables, and how to use data frames. I've introduced manipulating data frames a little bit, and we've talked about making our Markdown files for our reports and how we can, once we get all the R script set up, we can knit that and create a nice little HTML report from our R scripts. Okay.